ahead and get started, please. A couple of announcements. The exam is not quite finished being graded. Pretty close, not quite. It should definitely be back by Thursday. I feel pretty confident saying they will have it back by Thursday. From what I've seen so far, the grades are great. So certainly no worse than the last one. At least I haven't seen them all yet. So unless the ones that I haven't seen are just completely awful, I expect the grades to be about the same as they were last time. But I will give you more information about all that on Thursday and give you your exam back on Thursday. We're really trying to catch up on grading in general right now. We're a little bit behind, so you are probably going to see a lot of grades start to hit Blackboard over the next week or so. We've got a lot of stuff that we're trying to get finished up and get caught up on because we are in the last section, so there aren't very many assignments that are left. There's going to be, the next assignment is going to be given out maybe as soon as Thursday, definitely by Tuesday at the absolute latest. So you've got that to look forward to, and then there will be at least one more lab. I'm hoping for 2 labs. We're going to kind of wait and see how timing goes. I'm hoping for at least 1 lab and 1 written assignment, hopefully 2 labs. Trying to think if there's anything else that we need to discuss right now. Are there any questions for me about logistical things before we get started? Alrighty, so we are in the last section of the course. So we've got about 5 weeks left, 4 weeks left, something like that, if you don't count Thanksgiving. We are about wrapping things up here, and the major topic of this last section is going to be these high-level state machines. So I posted a video about this a few days back, about these high-level state machines. We are going to spend the next at least 2, maybe even 3 class periods just talking about how these things work, how do we design these things, how do we write Vhdl for these things, and then we're going to take these high-level state machines a few steps farther towards the end of the class and start to piece together actual components that you would find inside of a computer with them. So that is our ultimate goal over the next few weeks. So let's get started. First things first today, these high-level state machines are, in some ways very similar to finite state machines. In some ways they are very different. So we've got 3 different areas up here. Let's start with the actual diagram itself. If I look at a high-level state machine versus the finite state machine that we just spent all that time working on in the previous section of the course, what am I going to see that's different? Yeah?
Well, I mean, for one thing, high-level state machines have arithmetic expressions.
Yep. Right, so I can do addition, subtraction, and all that kind of fun stuff, right? Absolutely. What else am I going to see? Load register, yes. What does the load register represent in terms of so I don't see registers on my state diagram, right? What do I see those registers as part of my diagram? Yeah. Variables, right. So we can have variables in these things now, right? We haven't actually seen variables so much in the previous examples. We've had inputs and outputs, but now we can actually store variables in these registers and then use those registers to help us perform certain actions or perform certain transitions within our high-level state machine. Anything else? Anything else different from just from the diagram perspective? So we covered what, arithmetic, we covered variables, yeah. Yeah, so we saw on the, I believe the Zybook covered this, and we saw this on the lab as well, that there's a bit of a problem if we try to use the ands and or syntax that we've been using all semester long inside of these high-level state machines. So you're more likely to see, what you're used to from Java or C or whatever your language of choice is. These are going to represent the actual ands and ors in our high-level state machines so that we don't confuse them with the bitwise operations that we've seen previously. Or you might also see the actual word and or spelled out as well more often. So that's going to become more common. Yep. There are some things that are the same, though, right? For the most part. We still have states. We still have transitions. That's pretty much the same. We still have inputs, we still have outputs. What we do with those inputs and how we control those outputs, that's probably a little bit different, but they're still there. We still have them. Still need to pay attention to those kinds of things. Actually, kind of speaking on outputs, that's another important difference, right, with the high-level state machines. For starters, we're going to see a lot more mealy machines now than more machines. We saw a lot of more machines last time and a few mealy machines. We're going to be dealing a lot with mealy machines from here on out. But some of the examples with the mealy machines, so we saw the outputs on the transitions, right? But were they really outputs? What was happening? I guess there was just the one example in the slide, and then there was another example in the textbook, right? Or an example or two in the textbook. So what we saw is when we transition from one state to the next, we'd see, the condition, the transition condition, and then the slash, because it's a mealy machine. But here, we would expect to see an output, but it wasn't always an output, right? What might we see here instead? Yeah. Yeah, so we might see, I like to call them actions instead of outputs. We might see actions here instead. So we might be updating the value of a variable, right? We might be setting the value of a variable. We might be adding something to a variable. We might be reading in an input and storing it to a variable. We might be taking a variable and putting it into the output. Those are still valid actions, right? But this is no longer going to reference just outputs. It could reference something that's happening internally to the machine as well as the outputs, right? So these actions are going to become increasingly common too. Cool. I think that about covers it. So if we look at a circuit then, what am I going to see with the high-level state machine? What am I going to see in that circuit? Yeah, go ahead. Yep. Perfect. So our registers we need registers for our variables. We already talked about that part a little bit. The finite state machine itself is going to become a controller. So it's going to control what exactly? What am I controlling? Call it a controller. What's it controlling? Oh, what's the other piece that we talked about? It's controlling the register, right? So we decide when that register loads in a value. We decide when to increment that register. We decide when to decrement that register, to add something, multiply, whatever the operations are that are necessary, right? We can read the value out of that register if we need to and use that to set the output. So the controller is in charge of manipulating the control signals for the various registers so that they get the appropriate values at the appropriate times. Right? That's why we call it a controller, because it's sort of the manager of the entire circuit. Has to track all the different registers, make sure they have the right values. Okay, and then finally a Vhdl. This might be the easiest one of the three, actually. Do we expect to see much different in terms of Vhdl? The good news is no. The good news is, really, we know how to code finite state machines, right? That was the last section. That's not really going to change. The biggest difference in the Vhdl is just going to be there's going to be more stuff. There's going to be more variables, right, to hold the register to represent the registers in our circuits. So we do expect to see more variables, perhaps more arithmetic operations showing up, things of that nature. But there's nothing that we haven't already learned in Vhdl that needs to be explained to implement these things. So that's kind of a nice thing. We may introduce a few final Vhdl concepts to make our lives a little bit easier, but we do already know enough to implement these in Vhdl. Fantastic. Any questions on the difference or similarities between HighLevel versus the regular finite state machines before we move on? It's really important. Right? Okay, cool. So in the video then, we saw this HighLevel state machine. This is the one that I introduced you to in the video. And what this did was it counted pulses. At the very beginning of the operation of this state machine, we read in a value called n, right? And we store that to a variable. And then when we see n pulses, we set our output to be high, right? The problem with this, well, maybe it's a problem, maybe it's not. It depends on what you want to use it for. One potential issue with this is once, let's say n is 3, and I count 3 pulses, 3, 2, 1, right? I successfully change my output, but then I'm done. I can't count anything else after that. It's entirely finished at that point. The pulses can still come in, but I'm done counting. I'm done counting. So your first task is to take this and modify it such that when we are finished, right, we can go back and count all over again. Okay? Take a few minutes, talk to your neighbors. It shouldn't take you more than 5 minutes or so, right? If you have any questions about this diagram, if this diagram looks confusing to you, or you watch the video but you still don't quite get it, please flag me down so that we can get this sorted out, or Elliot. All right. Oh, I'm sorry. They were on the Xi book. Did I forget to put them on the calendar? That's totally my bad then. Okay, my fault. No, that's totally my fault. I didn't realize that I forgot to do that. Let me just double check and make. They were on the Xi book, right? They weren't 2 hours ago? Well, I definitely posted them earlier than 2 hours ago. Let me see what happened with that. So here it is. There was just one. There was just one. Okay, well that's all right. That's all right. I will just go ahead then and assume that we haven't seen the video yet. That's fine. Let's walk through this. Let's walk through this then as a group before we answer this question. Not a problem at all. So what's happening here? Let's start. I'm going to ignore this state for starters. I'm going to pretend like this state isn't here. We'll come back to it a little bit later. For starters, I'm going to pay attention to these 3 states. Right? So I've already told you what this machine, what I want this machine to do. I want it to count pulses. So I have an input, right? Inputs can go up and down. And when I see a pulse come through, right, which is an up followed by a down, this is one pulse, right? That is what I'm counting as one thing that is happening. And so this machine is going to count these things, and when I've seen a particular number, and that number can be anything, right? I get to decide what that number is. Then it's going to raise an output. It's going to say, hey, I've seen 3 pulses, or 10 pulses, or however many pulses you want. So let's take a look at how this works then. We start in the reset state. The first thing that we have to do, actually, it has nothing to do with the pulses. The first thing that we have to do is tell it how many pulses we're expecting. Tell it what those pulses are. So that's what this reset state is doing, right? It says take n is an input into this circuit, and store it in this variable called count. Count is then going to become a register, right? A register in our circuit, in Vhdl as well. And then we transition to this state. You'll notice that this dn input is what's actually going to be providing us with our pulses. So we notice here that dn is 0. So we are in this state. This state here represents that we have seen 0, right? That we have seen a low input. So we haven't really seen anything yet. We're just at the very beginning. Haven't seen anything yet. As long as this stays 0, we just kind of hang out. Spin and wait. As soon as we see a 1 come in, we'll transition to this state, right? And hang out in this state as long as we've seen a 1. And then as soon as it goes back to 0, that's going to complete the pulse, right? So you can actually see this is where we transition over to previous 1 from previous 0. And this is where we transition back to previous 0 from previous 1. Once this happens, right, we need to update our counter. If the counter is not equal to 0, then subtract 1 from the counter, right? So notice this is not an output, right? This is an action that takes place on the register. We just talked about that, right? This is not an output, right? And so we go back to previous 0, and then we just wait. We just wait for the next one. We do the whole process over again. So where is the actual output? Well, you see the output kind of hanging out down here at the bottom. It's not applied to a particular transition. It's actually applied to the entire state machine as a whole. Right? It says my output event is going to be 1 if the count is 0, if I don't have any more that I need to see, right? Otherwise, it's going to be 0. So if n is 3, I need to wait for 3 of these. Ooh, that's horrible. I need to wait for 3 of these complete cycles to pass. And then only at this point right here, the falling edge, will we see the output go high. Right? Does that make sense? Are there questions about how this works? So what's this state for then? I ignored this state at the beginning. So let's come back to it now. Actually, maybe somebody can tell me what that state is for. Do you see why we need that other state? What is it for? Yeah.
That's for if you begin while you're in the middle of the high.
Right. So we have no idea whether the input's going to be low or high at the beginning. It could be either, right? We only want to count it after it goes up and then down. But what happens if we start up? Then we need to wait for it to go down before we can actually begin counting. We need to wait for it to go down again. So that's what this state is for. It's doing the same thing on this transition, right? You see that I'm still reading in this value of n and storing it in my register, storing it in my variable. So you'll notice the input is high in this case. So we just kind of hang out here until we see the input go low again, and now we can begin counting the different pulses that come in. Right? Now we can start counting those. Cool. Any other questions about this? Yes? So absolutely it is going to have to be connected to a clock. There's no way that we can actually remember what we've done previously without a synchronous circuit. So you're right. It's implied that this low and this high that's being seen is on a clock edge. So if the pulse happens faster than the clock does, for example, we won't catch it. We won't see it, which is potentially a disadvantage to the circuit. But that's just it's kind of unavoidable. I'm not sure that there's a workaround for that. Great question. Any other questions about this HighLevel state machine? Okay, cool. Now, hopefully, we should be able to then take a look at this question, right? Or maybe somebody already thought of a solution while we were talking about it. They think of how we can fix this issue where once I count, if n is 3, right? Once I count 3 pulses, it's just done forever. How do I fix that? Yeah. So when count is 0, can I just transition back from previous 0 to reset? Actually, yes. I think you can even do that from here, right? You can do that from here. D in goes low. If count is 0, then go back to reset. Right? Go back to reset. That's really the only change we need to make. That's the only change that we need to make. Does everybody see that? Yeah.
Why are you doing it off the previous ones of previous 0?
Well, if I go back, it's only going to make maybe 1 clock cycle's worth of difference.
Yeah.
And I'm not sure that this would be the worst decision in the world. In fact, I'm sure it would work just fine. But this would be this would happen a little bit faster because I could. So what would this transition actually look like?
Yeah.
Well,
Previous one.
I see what you're saying.
It counts as 1.
Yeah, I see what you're saying. I see what you're saying. So they're equally as fast.
Yeah.
So I was mistaken earlier. You're absolutely right. You can do it from either one. Yep. No doubt about it. You can do it from either one.
Yeah, okay, because then it's 1 clock cycle faster. Otherwise, it's many clock cycles slower. You just assume the pulse is slower.
Yes. Yep. So for transitioning from previous 0, let's say, what does this transition actually look like? What am I looking for? I'm looking for count equals 0. Right? If count is equal to 0, then transition back to reset. Is that right? Do I need to do anything else? Do I need an action here? No. No, I don't think so because the rest of it's already taken care of for us. Reading in the value of that, that's already taken care of for us. It's not a problem. Not a problem at all. Cool. Any other questions before we move on? All right. So this one's a little bit trickier. We want to create a state diagram that's going to count pairs of pulses instead of just one pulse. So this is one item that we're counting. Now I want this to be one item that we're counting. Okay. So what do I need to do then to make that adjustment to this high level stage? Does anybody have any ideas? Can I do it with the same number of states that I have right now? What do you think? Do I need more states, or can I just add a few transitions or change the transitions that I have? Yeah.
Two things. Back on the previous slide, transitioning from previous one, that changes how the circuit works. Because you're going to go back to reset, no longer on the falling edge of the pulse. You're going to go back to reset while the pulse is still high.
Why is that? Could I not code up a condition that says count equals 0 and dn equals 0?
Yeah. Now.
Yeah. Yeah. The transition would have to be different, but you could do it. You could certainly do it.
And and then you just put it up here that you do need an action if you're going to do count equals 1. You need to set count equals 0 at some point for your output.
You are correct, or you could. Well, yeah, no, you're correct.
Or you could change if count equals 0 to that event. Is there a count equals 0?
Yeah. I think that my assumption of doing this on the previous one is actually a little bit more complicated than doing it on the previous 0. Yeah. I'm so glad we talked about it, though, right? There's certainly implications of doing it from different places. Maybe I'll give you a few minutes to talk this one out and think through this one. We'll talk about this in a few minutes. Please flag me down if you have any questions.
Because you're going to be sitting in, you're going to sit at
Oh, no, I didn't. I mean, I want this like
Also, did you see the number 6 with all the months and stuff?
the number 6 with all the money and stuff. I can't say that I did.
I think you remember if you did.
Probably so.
Because I saw
That's
that.
actually the only problem I have left to grade. Is number 6.
Okay.
Every other problem is finished except for
I saw that and I was like, I looked at it for a little bit and I was like, that's for sure.
Fair enough. Fair enough. Okay, so let's talk about this. I can think of at least 3 different ways to approach this problem, and I'm not sure if any are particularly better or worse than the other ones. But I think it's worth investigating them all to see, what the advantages and disadvantages might be. Does anybody have any suggestions for me in terms of what to do? Yeah. So that's one of the 3 that I was considering. Can we just multiply the initial input by 2? What do you guys think? Does anybody have a problem with that approach? Seems almost like cheating, right? Seems almost like too easy to get away with. I think the answer is sure. Yeah, absolutely. Why not? Why not? But what are the implications of that? There is one potential thing you would have to be aware of if you're going to go that route. You think of why, where, how the. Can you think of why that might cause a potential issue? Yeah.
Would you have to subtract 2 from 1?
No, the counts would still work out. Oh, counts will work out fine, right? Counts will work out okay. Think about it in terms of the circuit, the physical circuit. Are there any potential issues by doing it that way? Multiplication is not particularly easy compared to some of the other operations that we've seen. We haven't actually taken a look at multiplication yet. It takes a little bit more work. So
it's times 2, so it's just left shift 1.
It is just left shift 1. Yep, absolutely. Think about, maybe I've designed this circuit for, and I have this value count, right? Maybe count is a register with only 4 bits in it. And then I try to design this circuit to where count can take on 2 times n instead. Well, I can't represent the same number of counts with that register, right? That register is not going to be able to hold 2 times n as effectively as a larger register would, right? So if I'm interested in the size of my register, saying 2 times n here is going to necessitate using a bigger register, which is not necessarily a bad thing. It's just something that you need to be aware of if that's the approach that you're going to be taking. Yes?
Why if we're looking at pairs, they're looking at 2 times the rather than 2? They're looking at pairs.
So let's say n is 3, right? That means I need to see 6 pulses in total. So if n is 3, this is 1 pair, and then 2 pairs, and then 3 pairs would be 6 pulses total.
So we're saying measure of pairs, not the number of pairs.
Oh, right. Right. So in order to get the number of the total number of pulses that I need, I take in the number of pairs and I just multiply by 2. Right. That gets me the total number of pulses that I need. Yeah. So I think multiplying n by 2 here works. There are at least 2 other ways that I think you could approach this problem. So I'm interested in talking about those as well. Yes.
Create a new variable that is just a 1, 0 value, and only decrement count when this variable is either 0 or 1, depending on how you want to set it up.
Perfect.
And every single time you do the transition from previous 1 to previous 0, you flip the value of the new variable.
Perfect. So we'll initially set that value to be, what, 0, I guess, at the beginning?
0 or 1.
It doesn't really matter, right?
You just have to change your logic ever so slightly.
So the idea is create a new variable. It's just 1 bit, right, that indicates whether we've previously seen a pulse or not, basically, right? So have we already seen the first one, or are we looking at the first one now? Is what we're going to use that variable for. So that would indicate just 1 additional bit that we would then need to check as we transition back, right? If we've already seen a pair, if we've already seen the first item, then we've now seen 2 in a row, so we should decrease the count. If we haven't yet seen a pulse, this must be the first one, so don't touch count right now. We wouldn't need any additional states at all, right? We would just need to change this logic pretty significantly. Well, we need to change this logic and this logic and this logic. So we need to change quite a bit of logic on the transitions, but we wouldn't need to add any additional states. So that's a good thing, right? Yes. Yeah. Yeah. Yeah, so that's the third option that I had is just 2 additional states, right? Just basically take these states and copy them, and then this count only decreases when I go from this one over here back to this one, right? That's basically the other way about it. So, I mean, let's consider our options that, again, in terms of the physical circuit that we're designing itself, adding an additional variable, remember it's just a 1-bit variable, that's a lot less than potentially having to put a giant register on there to keep 2 times n. So 2 times n is really simple. I think the variable one is fairly simple as well. It's not particularly complicated. And in terms of storage space, we take up less, although the additional logic may negate that to some extent.
The 2 times n isn't that just as much additional circuitry as the variable? Because if you have a 4-bit register, you now need a 5-bit register. But a 5-bit register probably doesn't readily exist.
Yeah, 5-bit register. We haven't talked about that, but you're right. 5-bit registers aren't really a real thing that happens. Registers usually come in powers of 2, so
yeah.
Typically, so you'd be going from a 4-bit register to an 8-bit register. I mean, but again, like I said, the logic, the changes in logic here on the transitions are also going to have an effect on our circuit in terms of how many gates, in terms of what that looks like. So it's kind of apples to oranges to some degree. It's not easy to make a direct comparison between the two. What effect does adding 2 additional states do? What effect does that have? Our register stays the same, right? Basically, the register doesn't change at all. Our logic doesn't really change a whole lot either. Yeah.
You just need more flip-flops for your state.
We need more flip-flops for our state because right now I've got 4 states, so I can actually do that in 2 flip-flops if I want to. As soon as I add another state on here, do I need at least 3 to make it happen? So it's an additional flip-flop at least. If I'm doing 1-hot encoding, it would be 2 additional flip-flops, right? So, you know, either way, you're adding on at least a little bit of storage to make this happen. Now, are you storing larger values per count? Are you storing an additional variable? Are you storing additional states? Well, it's kind of up to you. There's trade-offs in all of those. Just be aware of how those changes are going to affect your underlying circuit. That's kind of the moral of this. Were there any other options for changing this that I didn't consider that somebody else thought of? No? Any questions about this problem? That was good. I like that. All right, and so again, assuming that you haven't seen the video yet, let's run through this Vhdl. This is the Vhdl for the original circuit, the original high-level state machine, not any of the modified versions that we've been talking about. So let's point out what's the same and what's different. You'll notice at the top we've got some similarities. Define your states, right? Define a signal to stash those states or a variable, doesn't matter. In that particular case. Here, we also have a register, so we have that variable count now, right? That is a register. How big this is, I mean, in this case, we chose it as 3 bits. That was kind of arbitrary, right? It depends on what your limitations are as a circuit designer, how big that register needs to be. In this case, these 4 bits limit us to limit the count, the counter to count how many values, how many pulses? 16 maximum, right? You can't count any more than 16 pulses. So, or I guess actually 15, right? Because 1 is 15. Right. 16 unique values, but once we hit 0, it doesn't really matter anymore. Yeah. So if I want to count more than that, I need to make that larger. But that's not a hard thing to do. And then we go into our process. Here's our reset logic. That's the same. That hasn't changed from the finite state machines that we know. The state transitions are here, and these are going to start looking different. You'll notice I've got if statements embedded inside my case-blend statements. We haven't seen any examples of that before, although some of you did do that on the exam, which is fine. I'm not knocking it. I'm just saying some of you have already considered this as a potential option. That's a good thing because we're going to start doing this more often now. And so we see that the transitions are dependent on not just the inputs, D is our input, right? But also the registers. So we can see, right, if count is not equal to 0, then count is count minus 1. That's actually not a transition. That's an action that's taking place. That's one of the actions that we talked about. Trying to think if there's anything else I need to point out. And then here's the output down here. Event is 1 when count is 0, otherwise it's 0. Right. So, let's see. I'm trying to think if there's anything that I need to discuss here that I didn't do. Are there any questions about this? Anything that looks weird or funky to you that you want to talk about in more detail? Okay, let's talk about this problem now, right? So the problem wants us to modify this Vhdl to implement the paired counter that we just discussed. So we can talk about that in 3 different ways, right? The first way was to multiply a count by 2. That's easy. That would happen right here, right? Just multiply n by 2 as it's coming in. But we also discussed that we almost definitely want to make this wider. We want to make that count variable wider if that's something that we did. What was option 2? Option 2 was to add a variable in, so that would actually change quite a bit of the VHDL. That might be the most drastic change to the VHDL if that was the case that you chose. So you would have to check here, right? You'd have to check the value of that previous variable as well as your counter before making any decisions. What was the third option? Oh, additional states was the third option, right? So that would indicate that we would need more when statements. We need to modify additional states. That would actually be a pretty... That's true. Yeah, that's true. You'd have to add the states to your type definition and then basically replicate these 2 things, but this piece would only go, this piece would take you back to the very first one. Yep. It wouldn't be that bad. It would not be that bad. I'm not going to spend a whole ton of time on this today because we're going to spend a lot of time talking about VHDL, probably on there. Actually, we'll see more VHDL a little bit later today as well. Are there any questions on this right now? Or do we want the next one? All right, cool. Let's take a look at a new problem. So, oh wait, before we take a look at a new problem, hang on. One step ahead of myself. So one of the things we talked about in the previous section was how do we design finite state machines, right? I kind of want to rethink that process with high-level state machines in mind. A lot of it's going to be similar, maybe even exactly the same, but there are some important differences. So what were the steps then for designing finite state machines that we talked about in the previous section? Yeah. So inputs and outputs was one of the first things that we talked about, right? Inputs and outputs. Let me write these down. Do we need to change the way that we think about inputs and outputs with high-level state machines versus the finite state machines that we've seen before? What might be different? Yeah, go ahead. Right, so our inputs and outputs are more likely to be multi-bit inputs and outputs than with the simple finite state machines that we saw previously. I think that's about it, really. There's not a whole lot of change. We still need to do this step, right? We still need to know what the inputs are, what the outputs are. That's not going to change. We just need to realize that the inputs and outputs might be a little bit larger. They're not going to be single bit anymore. What else? What was another step that we had to consider when designing finite state machines? Yeah, in the back. Identify the states and transitions. So actually, the way that this was stated was determine, hang on. The way this was stated in the video was, what do we have to remember? What do we have to remember, right? That's how it was stated in the video. So the answer to this question before today was, ultimately going to become our states. And that's still true, right? Some of the answers to this question will become states. However, there's also a new additional potential thing that we can do with the answers to this question as well. Does anybody kind of get the gist of what I'm talking about? What else are we remembering in our high-level state machines? We weren't necessarily worried about it in finite state machines. Yeah. Variables, right? So the answer to this question might be a state. It might be a variable. And now we kind of have to try and distinguish the two somehow. It's a tough distinction sometimes, right? It's a tough distinction. I'll try and help you out. If you're unsure whether it should be a variable versus a state or potentially a set of states, consider how many values that variable could take on. If it's a pretty small amount of values, a state might be appropriate. I don't want to give a definitive, right, say state, then it should be a state. If it's got a large amount of values that it could potentially have, think about count, right? Count is a horrible candidate for states. Could you do it? Yeah, but oh my gosh, no thank you. So if the thing that you're remembering could have a potentially large amount of values, that's probably going to be a variable. If it's got a few amount of values, it might still be a variable, but it's at least a candidate to be a state, potentially as well, right? In fact, we saw that on the previous example with the pair pulse counting, where we could represent the previous pair as either an additional set of states or a variable, right? Sometimes it can go both ways. That's not necessarily a problem. Okay. And so the other piece actually that was mentioned was the transitions, right? And transitions are pretty significantly different under this scheme, right? So how do we need to think about transitions now? Let's talk about that a little bit. Talked about this a bit at the beginning. How do we think about transitions now versus the finite state machines that we saw earlier? What are the transitions going to be acting upon? Inputs, right? That's still true. It still depends on state and input, but that's not all, right? That's not all anymore. Now it also could potentially depend on our variables. It could also depend on what those values are. So these two we've already been using. This one is new to high-level state machines, so it makes things a little bit different. And then also with transitions, right? Also with the other different thing we talked about transitions are these actions, which may be the same as we saw before. It might be setting the output. That could potentially be something that we do. But it might also be setting a variable. Or it might be some kind of arithmetic that needs to take place. These we haven't seen before, right? This we've done. These are new. These are new to our high level stage. So the design process is really pretty much the same. There's just a few extra considerations that we now need to take into account when we're designing these high level state machines versus the traditional finite state machines. This is going to be tough. I'm not going to try and sugarcoat it for you guys. The first couple of times I ask you to write one of these things down, it's going to be kind of hard to wrap your mind around it, especially since you're already in this mode of thinking about the old way of doing things. But we'll keep practicing it until we get it right. And so then once we have this, we can, of course, turn that into a Vhdl. One thing that I also kind of want you to think about that we're going to start seeing is we may eventually stop explicitly putting states into Vhdl. It may not be necessary anymore. The states might just be the values of our variables. The values of the variables themselves might be our states, in which case we no longer have to say type state type is states. We'll actually have an example of that we'll see either today or Thursday if we're running out of time. Any questions about this design process before I turn you loose on one of these things? Before we try one out? Okay, let's try one out. So on the FPGA, we've got buttons. We had to use the buttons on a couple of labs, right? So the buttons, one of the pains about buttons is that when I push them down, the contacts tend to jitter a little bit. They tend to vibrate against one another. And so it can look like, even though I, the human, am pressing the button once, in terms of the electric pulses that come in through the circuit, it may look like we pushed that button a bunch of times. So how do we fix that problem? How do we make it so that even if there's some jitter involved, even if there's a little bit of jitter involved, the button is only registered as being pressed once instead of a whole bunch of times? This is called debouncing, because the button is literally bouncing against the contacts when you push it down. We want to debounce it so it looks like it just happened the one time. The way that this is typically done, I'll give you some hints here, is we have this value called delta. And if the input has remained stable for some time delta, then we allow that input to be the output. Right? And that goes whether the input is high or whether the input is low. Right? So if the input changes at some point, then we reset delta. We have to wait. So we need a whole cycle of delta to occur before we can assume that this input is stable. Does that make sense? So your task is to design a high-level state machine for a button debouncer. Consider what's our input. This is our input, right? The input. What's our output? We just have one output. So it's just one input and one output. One input, one output. That's pretty simple. Think about how many states you need. Think about if you need any extra variables, what those might look like. Right? We can assume that delta is going to be some constant in this, so we don't have to read it in from the outside like we do with the pulse counter and n. We don't have to worry about that. Assume delta is just some constant value in this particular case. Take a few minutes, talk to your neighbors, see if you can figure it out. It does not take a bunch of states. If you are finding yourself creating lots and lots of states, then reconsider your approach. And we'll talk about the answer in a little bit. Okay, here's a hint for you. These are the only two states that I need. Good job done. Leave their names. So, see if you can figure out what the transitions might be.
was your, did you have a different, don't need a variable. Use your state subtract the previous value, I see.
Yeah, and then you put the output value of
Oh, okay. No, I could see that work. We might actually try it that way as well.
Okay, let's see if we can figure this one out. It's not easy. I know there's only two states, but it's not an easy problem. I don't want to try and make you think that this is a particularly simple thing to solve, especially since we just started working with these high-level state machines today. So before I write down the transitions, I might also want to think of what other pieces I need. I don't need any other states. I'm gonna cap us at these two states. But what other pieces might I need in order to make this work? What might my transitions need to do the job? In other words, yeah. So I'll need a counter variable. Yes, you're absolutely right. I'm going to need a counter variable, so I'm going to write that over here. No, you're absolutely right. You're going to need a counter. So I'll just call it count. Do I need any other variables to make this function? Okay. Definitely need a counter. Anything else? So let's just try it out. We may find that we need something else later. We can always add that later on if we need to. So then I've got this variable. I've got these two states. We can start trying to piece some transitions together. What might transition? Somebody help me out here with that transition. I don't care what it is. Hook me up with the transition. Yeah.
When your count equals delta and you had an input, we'll switch from one to the other.
When count equals delta,
So it's been with that amount of time, and your input is one, so like your kill on your button, and it considers it to be pressed, so it'll move from one to the other.
move from one state to the other, from pending to stable. So what do I write here? Count equals delta,
And you have an input, so like, and you're actually like pressing.
and n equals 1. Okay? Out would be 1. And then count would have to reset to 0. Oops. Okay? Okay? I'm with you so far. So then what else do we need to make this happen? We must have another one that goes back in the opposite direction, right? That's going to actually be pretty similar to this one. I assume. I could be, this is deviating from what I had, so you guys are kind of in the driver's seat.
Yeah. We did basically the exact same thing, except input would be 0.
Uh-huh.
Transition, count equals delta, and then your output would go to
Count equal delta and n equals 0.
and out goes to 0, and the counter resets to 0.
Out goes to 0, count goes to 0. Okay? We're not done yet, right? So what else do we need? Two self loops, and what are these self loops going to do?
One of them is going to basically reset your counter if the input changes from what you want it to be, right?
So here we want it to be 0, right?
Right. So if the input is 1, then count goes back to 0. All that.
So if n is 1, then count goes back to 0.
And then otherwise, if input is 1, then counter is just counter plus 1.
If n is 0, right, over here.
Yeah.
Else.
Sorry, I was
Yeah, that's okay. Count plus 1. And then it's just the opposite over here, right? Yeah, I see what you're saying. So if the input is 1, then we reset our counter because we need to start over from scratch. Otherwise, count is going to go from count to count is going to go to count plus 1. I see. And then over here we have another one that does the same thing. It says, if int is 0, count is 0, else count is count plus 1. So these names aren't really appropriate. This is looking for 1 or looking for 1, and this one's looking for 0. Perhaps better ways of thinking about these states. It's not working well. Okay. I'm trying to think if there are any issues with this. I'm not coming up with any. Are there any questions, or does anybody see any issues with this? Yeah.
The one thing to take into account is that your constant implementing count, you need to only do that when count is less than delta. Actually,
You only need to do that when count is less than. Well, as soon as count hits delta, I'm going to come over.
Yeah.
I guess to be extra safe, we could say greater than or equal to delta here, just to be super safe. Right. In case we do happen to overcount, we just want to cover our bases. So here's my issue with this, which is where do we start? What's our start state? So this is looking for 1, right? So we're assuming that the input's going to be 0 at the start. If we assume that the input could be anything at the start, so this doesn't work. Yeah. No. That's the only thing. That's the only issue I have. And I think it's great. Besides that one little piece. Do we have any other questions or comments on this one? I'm happy to show you what I've got written down on my notes as well. I want to make sure. Do you have any questions or comments on this one first? I actually think this is good. I think this is a good high-level state machine. I think you could do this as long as you somehow enforce that assumption that it's always low. Or you might not even have to enforce it. You might just have to say you can use this as long as you know that we always start low or we always start high. Which you're the circuit designer. You are allowed to say stuff like that as long as you can justify your decisions. Let me show you what I've got. So I had 2 states called depending and stable. And the way that this finite state machine works is that all of the counting, right, all of the waiting until we hit delta happens in this state. And then once we've triggered delta, once we've kept things for time period delta, we move over here and we just hang out here until we see that it changes again, right? That we break delta. So with that in mind, we need to have some way of detecting whether the output's changed or not, right? We still need to count. So count is still a thing that exists. Count is still a thing that we need. But we also need a way of detecting whether the input is changed or not, whether it's different. And different could mean from 0 going to 1 or 1 going to 0. This is much more general, right? It could be either way, 0 going to 1 or 1 going to 0. So any ideas how we can accomplish that? How can we determine if the input is changed somehow? I don't care how it's changed. I just want to know that it's changed. What does that look like? Yeah. Yep. So I just need another variable here, previous, right? That just remembers what the previous value of my input was. Okay. And so what pending is going to be doing is constantly checking this, right? If previous is this, if the previous value is the same as it was before, then I can increase counts, right? Otherwise, I need to reset counts back to 0 and start all over again. So I use a little bit of shorthand on mine so that I don't have to keep writing this variable out all over the place. Let me show you what I mean by that. So here, right, if we determine that the input is stabilizing, right, I'm just going to say no change to the input, then count is count plus 1. If we detect a change, so this is another self loop. If we detect a change, then count goes to 0. And then for this transition from pending to stable, that's going to be based on the fact that things have not changed and count is equal to delta. Yeah. Actually, so I kind of screwed up. In my notes, I actually have this counting down, starting at delta and counting down to 0, but on this one, I started at 0 and count up to delta. It can be done either way. That's not particularly important, right? It works both directions. So then stable has a transition back that says if I detect a change, then count goes to 0. We're almost done. We also have a self loop here that says no change. Now the only thing that I'm missing is my output. What should my output be? Where should I worry about output? So output's more generic now, right? I don't know what my, nowhere in here do I care whether my input is 1 or 0. Nowhere in here do I ever check to see whether the input is 1 or 0. That's not my problem. I'm only worried about if the input changes or if it doesn't change. That's all I'm worried about, right? So what does that mean in terms of the output? Yeah?
On your transition to stable, you set your output equal to n.
Yep, perfect. Out is going to be equal to n. So I need a slash, right? Perfect. Done. Done deal. I don't need to worry about anything else. Yeah? Nope. Not at all. That's perfectly okay. Count plus plus is fine. So in terms of the diagram, I'm not sure that I would worry about that necessarily. In terms of the Vhdl, I'm actually about to show you the Vhdl for this, so I'll show you exactly how it's coded up in just a few minutes. Are there any questions on the diagram before we get to the Vhdl? So I do want to show you the Vhdl. Actually, some of you I know have already seen it, have already asked me questions about it, have already played around with it. You already have access to the Vhdl for this. Right? It was given to you in both of the previous labs because we've used buttons. We've used buttons in the previous lab. So this exact high-level state machine has already been given to you. You've already used it. So now is a good time to take a look at it and see how it actually works. Let's just take a peek at it together and see what this looks like. Where's my mouse? Oh, there it is. So I've already got it opened up. Let me just make it a little bit bigger. So debouncer. The debouncer VHD file that was in the zip file of stuff that I've given to you on the previous labs contains an implementation of this exact high-level state machine. Could you have done it the other way we had up on the board? Certainly, certainly. But I wanted to show you this way because this way matches up with the code that you have already. So one thing that we see up here that we haven't necessarily seen before are generics. Have you guys dealt with generics in Java? What class are generics?
covered until later on. Actually,
Has anybody seen generics before?
did y'all ever see?
Okay, not a problem. Not a problem at all. What we are using this for is to define a design property, I'll call it, called width. So how many bits are we using for these values? How many bits are we using for our inputs and outputs? I want to be able to debounce, right? Sometimes 4 buttons, sometimes 8 buttons, sometimes 32 buttons. And so I want this to be able to accommodate all of those different configurations. I don't want to have to create a new one for 4 buttons and another one for 8 buttons, right? So by using this generic, it just allows me, gives me some flexibility. If I want to change this for different values, I just have to change the width. That's all. That's all that's there for. So I define my entity. Of course, it's based on the clock. Here's my input. Here's my output. Right? We see that they're actually. Wait a second. Am I in the right file? No, I'm in the right file. And so here is our variable, or 2 variables, as a matter of fact, our previous value. So previous and count for delta. I did mention that actually we're counting down in this file. On the board I have it as counting up, but on the code I think we're actually counting down. It's a pretty small change. So what do? The first thing I do is I record my previous value. So on the rising edge, right, I record my previous value. If the previous value is not equal to the current value, then reset the counter. That's what's happening here, right? We're setting everything to be high, so we're actually setting it to be delta, not setting it to be 0, since this is counting down. Otherwise, if the count is not already hit 0, so this is a little bit new syntax. Count range is a shorthand way of checking all of the bits to make sure that they hit 0, right? So we're checking all of the bits. So count apostrophe range is just an easier way of saying if count is not equal to 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Right? Then we are going to decrease count by 1. That's what it says over here. Otherwise, so if these previous conditions are false, if previous output does match, if the count is 0, then we must have hit delta. So set the output to be what the input is. Yes?
You set previous in to in, and then check if previous in equals in. Won't that condition always be true?
I set previous in to be in, and then check if previous in is not equal to in.
Like how is that if not always true?
Right. No, I understand what you're saying. So the way that this is going to, let me think about this for a second. No, it's a valid question. I just want to make sure that I answer it appropriately.
Like VHDL is strange in the fact that my brain thinks of code as serial, but VHDL doesn't do things.
So, one thing that is that we need to pay attention to here is that previous DN is only ever going to change on the rising edge of the clock, right? Whereas DN can change at any time whatsoever. It is not bound to the clock at 1 bit at any point. DN can change whenever it wants to, absolutely no matter what. So I think that's actually part of what helps us here in differentiating the two. Even though it does look like we are immediately comparing, we set them and then we immediately compare right away to see if they're not equal to one another. The fact that DN can change immediately, whereas at any point in time, whereas this can only change on the rising edge of the clock, means that even though there is an instant of time where they are guaranteed to be equal to one another, DN can change immediately after. Yeah, you have a question?
Well, I was going to say, can you just put that assignment previously in after the, like, if else?
You could, sure. You could, sure. I'm still not convinced that it is a problem necessarily because
We've been using this.
you've been using this code and it's worked.
It clearly works. I'm just curious as like what part of VHDL makes it
It has to go, it goes back to the fact that this is a register, so it's only going to update on the right edge of the clock, whereas this is going to change it at any possible point in time. Is what it goes back to. Yep. But if this makes you feel better about it, I don't think this actually changes anything in terms of functionality-wise. Although I want to test it before I make such a statement, I suppose. But let me point out a couple of other important features about this VHDL. For starters, do you notice any states? I've got 2 states here on the board. Where are they? Where are those states? They don't exist. They don't exist. So that's something that is perhaps a little bit frustrating, especially considering how we've constructed finite state machines in the past. But from here on out, we may very well put a finite state machine up on the board or write it down on a sheet of paper and then never create actual states in our code at all. It's not necessary. It's not entirely required to do so. Does that mean this is not a finite state machine? No, not necessarily. Not necessarily. What is defining our states here? How do we know what state we're in? Yeah. The value of count is determining exactly what state we're in, right? If count is equal to delta, I know I'm in the stable state. If count is anything else, I know that I'm in this state, right? So the value of count is determining what state I'm in. It is not necessary for me to make that explicit. It's not a required thing that we have to do. In fact, the code ends up being significantly simpler by leaving it out, leaving those states out. Am I going to count you wrong if you create states in the way that we've done it before? Absolutely not. Absolutely not. So if it makes you feel comfortable to keep doing things that way, by all means, go right ahead. But there may be simpler answers by leaving the states out. And we're going to see more examples of stuff like this over the next couple of weeks. Are there any other questions? I've got another example like this, but we only have 5 minutes left, so we're not going to have time to get to it today. I'm going to put that off until Thursday. Anybody have any questions for me? All right, we'll go ahead and call it a day. I will see you guys on Thursday.